We should start by mentioning the difficulties and major uncertainties in projecting sea level in terms of contributions from glacier melt. Okay, so prediction of sea level rise that results from it have two major challenges and uncertainties right now. We have to be careful when we say this because it can be used by skeptics, etc. But science is science. We have to do science and accept that there are uncertainties and that we are working on it to reduce uncertainties, right? The rate at which our emission of greenhouse gases into the atmosphere will continue to increase and warm the planet, especially at local scales, Antarctica versus Greenland, and how Arctic warming will affect the jet stream and the winter temperatures over Greenland, tropical, extratropical connections in terms of warm air mass movements and so on. Those are still a little bit uncertain, and the physics continues to improve every day and models continue to get better every day. The rate at which ice sheets and glaciers will respond to climate warming and collapse, which depends on physical processes that have not been fully elucidated and incorporated into physical climate models. So the previous projections, for example, many models didn't have land ice explicitly. It was dealt with in an indirect way. Obviously, that does add uncertainty to the sea level rise projections, but there are also other issues. Even if Mumbai is projected to have 1 meter sea level rise, can the city afford to protect against 1 meter sea level rise, or does it decide it based on the amount of resources it can raise to protect against sea level rise? So there is our social transformation, technological transformation, natural solutions, human behavior, etc. coming into picture. Okay, so here is our historic measure of sea level rise equivalent in millimeters and ice mass loss in gigatons. So these are positive numbers, but they are losses. So you can see here Greenland ice sheet cumulative ice mass loss is larger than Antarctic ice sheet cumulative ice mass loss. So Greenland has been accelerating. We will see some differences in the circulations, as I mentioned, and there is also the so-called polar amplification in the Arctic, which contributes, which I will show a figure of. And Antarctica, as I said, is complicated. To add a little bit of detail, Southern Ocean, which goes around it, can in some ways protect it against the quick exchange with the rest of the globe. I won't go into the dynamics right now, but warming of the Southern Ocean, which is less than, let's say, the Arctic because of, again, details which include ozone hole and the reduced ice albedo feedback, which is very large in the Arctic compared to the Antarctic. Warmer ocean can melt shelf ice and so on, as we will see from below. But warmer ocean can also warm the atmosphere, increase humidity, and increase snowfall in some parts of Antarctica. So we have to be very careful to see which part of Antarctica is really unstable and vulnerable to collapse versus which parts are actually doing okay. So this gives you a little bit sense of that, looking at a typical glacier, which has a equilibrium point here. It can go on both sides where glacier flows. So you can think of this as Greenland, which is land which is connected to the Atlantic Ocean and Labrador Sea and the Arctic Ocean on different sides, whereas the Antarctica is surrounded by the Southern Ocean, and it has huge amounts of glaciers that flow onto the ocean and become the so-called ice shelves. So the processes of melting and calving of ice shelves and how that affects glacier discharge and glacier movement are going to be very critical in Antarctica. So Antarctica has ice shelves with subglacial melting, so that's below by the warming ocean. Icebergs carve off from ice shelves, as we see here. You can see a little iceberg setting off here, and there is a little iceberg here over Greenland, where melting on the lower part of the surface, icebergs carve off from ice sheet edges into the sea, into ice fjords and the ocean. Atlantic, Labrador, Greenland, Norwegian, Iceland seas around it, right? So the processes are very different, much more of an ocean impact here than here, and this is accelerating as we just saw. So there is the ablation region, and there is the glacier flow happening. So there is the equilibrium line where there is snow accumulation here and there is ablation here. So more loss than accumulation. So Greenland is discharging about 300 gigatons per year, whereas this is the river discharge. So it's actually the glacier melt that is flowing off as water, the figure we saw before of the Mulan. That's pretty massive. And the ice discharge or a glacier discharge as icebergs and so on is about 300 gigaton per year. Whereas in Antarctica, there is not much of a glacier river discharge, water discharge happening, but there is glacier and ice discharge happening at 2200 gigatons per year. Okay, so the sea level rise contributions actually tend to be low near where the glaciers are, because the land that is being pushed down by the glacier is going to rise when glacier mass reduces, so sea level relatively drops. So sea level is going to be actually higher away from the glaciers. So the caption of this figure, which is quite complicated looking, is that the Greenland and Antarctic ice sheets form from the slow accumulation of snowfall. We'll see that it takes a long time to build glaciers, so if we lose them, they will not recover in human lifetime, which densifies into ice, which deforms under its own weight, makes it flow. Snowfall at the poles is low by global standards. Obviously they are dry, cold air, low moisture, very low precipitation. 24 centimeters per year in Greenland and 17 centimeters per year over Antarctica, compared to average of 1 meter per year around the globe. Okay, of course there are deserts and monsoons which are very high, very low. However, Greenland ice sheet contains enough ice to raise global sea level by 7 meters, and that figure is 56 meters for Antarctica. When 360 gigaton of ice melts in the ocean, that raises sea level by 1 millimeter. 1 gigaton is the amount of water consumed by a large city like LA in a whole year. Transfer of mass by the glaciers and the amount of melt at the surface are measured in gigatons per year. R is the annual runoff production. D is the annual discharge of ice for the ice sheets, average for the years 1961 to 1990 in these figures here. So you can see the difference of the climate drivers and the responses over Greenland and Antarctica. So we'll see how ice is melting. We already mentioned the formation of these ponds, which accelerate the warming because the albedo drops. You can see this looks much darker than the surrounding snow and ice. So that's going to absorb lots of energy. This can reject almost 90% or more, depending on how clean the ice is and whether it's snow or ice and so on. This, on the other hand, keeps more than 90% of the energy and only reflects 10%. So that's going to be a big deal. This is how ice albedo feedback looks. Okay, if there is some driver that increases temperature, like global warming, increase greenhouse gases. This is for the Arctic, but it applies for Antarctica and Greenland as well. Arctic ice melts, darker surface is revealed, albedo is reduced, reflectivity of the sunlight, which is the energy coming in, is absorbed more, right? So less reflectance of the surface. That increases absorption of solar radiation, which further increases the temperature, and you have a positive feedback. Okay, so as we said, in the melting phase, it goes really fast, abrupt. We know that around 12,000 years ago, things rapidly changed from refreezing to melting in the order of 10 years. That is really fast for climate processes, right? Especially when you consider the sea level equivalent of large chunks of icebergs breaking off and melting. Okay. On the glacier formation process, this will become slower because as temperature cools and glaciers or sea ice begins to build, temperatures cool further because reflectivity goes up, but colder temperatures hold less moisture. So the process of freezing or on glaciers, the snowfall decreases. So glacier building takes 100,000 years or longer, depending on how large and how thick it is. But melting goes really fast, order decades to centuries. So we are in the melting phase, so we are in the potentially abrupt collapse direction. This is why we have to worry about this. Okay?